Let's now talk about two more things about the introduction, and then we'll start a review for the math. And in this course, we're going to focus on building models, meaning that we're going to focus on building abstract descriptions of your system. Let's take a look. So modeling, coming up with abstract description of your system, and also formal reasoning, meaning that conducting mathematical proof, should be performed before you actually start coding. That's really the mindset we would like to convince you in this course. Before you dive into building Java code, well, we're talking about big system, right? If you're only building some very simple methods like what you did in 2030 or 1021, in that case, maybe you don't really need a model, right? But when you build even medium size or maybe large scale system, it will be much more cost effective if you try to build some model, some abstract descriptions, or maybe a series of abstract descriptions and do their proofs before you actually do the final implementation. It might be more cost effective. Okay. The idea would be once you if you start coding right away, doing verification would be would be just infeasible because your implementation itself might contain just too many details for you to actually consider for the proofs. All right, let's now talk about some ideas, some bullet points over here, and we'll definitely reiterate every bullet points over here as we go for the case study throughout the course. So for today, it's only for giving you some idea and keep in mind. A system's model it's abstraction. So the word abstraction is just about filtering out irrelevant detail. As far as the proof and system properties are concerned, what kind of detail should we put into the abstract description? So that'll be the question we have to keep asking ourselves. The tip of building the accurate model for your system is about thinking about what kind of a property do I really want to prove about a system. In that case, accordingly, we will build a model accordingly. Right? That's something we'll see later. And this is a very important analogy for you to remember. Okay, a system model means just as much as to a software engineer, who is you, as a blueprint means to a system architect. Whenever a system architect builds a house, they definitely have to make sure they got a very rigorous blueprint. For you as a software engineer, whenever you're trying to build a system that's safety critical, of course you want to make sure you have a reliable system model. Hopefully that has been proved already. Hopefully that has been provably correct. All right, it's a very important illustration I want to do right away. So in this course, we're going to say for a particular system, we may have a list, not just a single model, but we may have a series of models. Okay, and we may have a list of models sorted by accuracy. So what do I mean? Okay, let me just illustrate to you. Let's say we got index from 0 to all the way to n. So we got n plus 1 models, right? Just as an example. So here we got model-based developments. Meaning that your development is going to be based on models. A series of models, not just a single one. Okay, let's take a look. So you can think about this will be your first system model. Let me call it M0. And then, so this will be the most abstract. Or think about containing the least amount of details. Amount of details. And most importantly, usually once you come up with the simplest model or the most abstract model, you can already prove certain property. Easy to, or I should say easiest, it's kind of relative, right? Because we're going to have a series of model. Okay, easiest to prove some property. Okay, just remember that eventually we're going to have a pipeline of models along the developments of your system, but we definitely start with something that's the simplest, that's the most abstract. Okay, and then the idea would be we will actually go with a process called refinements. Okay, so M0 over here is going to be so-called refined by another model for the same system, M1. Okay, it's relative. So we say that M1 is a refinement of M0. Okay, that's another way to say it. You can say either say M0 is refined by M1, or you can say M1 is a refinement of M0. Let me say that as well. A refinements of M0. All right, and of course you can kind of imagine that. So conceptually, M1 is going to contain it's kind of relative. Since we say M0 is the most abstract, it cannot be more more abstract than that. So this will be a little bit more concrete. More, okay? Notice I said more rather than most. More concrete than M0. Okay? Meaning that it contains more details. And usually when we say contains more detail, one example can be you just add more variables to the model, right? Just by making your model more sophisticated. Okay, all right. And then what should you prove? Whenever you want to do proof, it will be important to also prove some property. Let's not mention this. Okay, but what I mentioned is the middle line over here. Over here, when you say M1 is actually refinements of M0, it will only be valid refinements if certain refinement obligation can be proved. That's something we also talk about as we go for the case study, right? To be a valid refinements, some proofs need to be done. Right? To be a valid refinements, right? Of course, we're gonna need the help from the tool as well later. So far, I only talk about two system models. Of course, it's gonna be a pipeline. So you can imagine that if I go with the sequence, it could be that M1 is actually going to go for maybe a long way, all the way to the final one. Maybe that's M by index n over here. And let's now just complete the picture over here. So now over here, this will be the most concrete. Okay, so contains the most detail. So this will be the closest to actual code. Not exactly the actual code, but it will be close enough. All right. So what's the idea over here? So the idea will be you got a series of system model from M0 all the way to Mn, right? So we got M+1 models. M+1 models for the same system, right? So the advantage of doing this is whenever you go from one model to another, you make sure you actually prove the refinements. And from one to another, you also prove the refinement. So there will be a series of refinements that you have to discharge. And discharging refinement rules, in many cases, actually much easier than if you simply want to verify the final code, right? I want you to think about scenario number 1 over here. Scenario number 1, which is about building different models and also prove the refinements, right? That's one way to go. And think about scenario number 2. What if we don't have the model-based approach? Scenario number 2. Let's say we don't have the model-based approach. In that case, we're simply going to build a large cluster of Java classes implementation, right? Well, for large-scale projects, don't be too surprised if you got dozens of classes or even close to 100 classes. In that case, verifying directly this large number of classes would be almost infeasible. So it'll be much easier if we go by the following. We say we actually build from simple until complicated model and prove the refinements between them, and then the final model is actually close enough to the actual code, in which case we can definitely base our coding on this final model, as opposed to we simply dive into coding without any models. In that case, after you have done your developments, if you really want to prove mathematically about the correctness of all these classes, it will just be infeasible. Okay, let me just write it down, and then we are done. Okay, infeasible. Infeasible to prove directly these classes. On the other hand, if we actually got this final model over here that is close enough to the code, so this will be actually the basis, because we know up to now every refinement step has been proved. So we know MN is actually consistent with our very initial model, and this also is close enough to the final code, so we will be able to base that for our our coding. Okay, basis for coding. And then once we are done with the code, we don't need to verify the final code anymore, because we know that it's actually based on some mathematically proved model over here. All right, that's about the big picture. So I might just revisit this picture again, but I think you deserve to actually know that right at the front, but may not be exactly understanding what's going on over here. But as we do case studies, I'll try to revisit the point whenever possible. All right, let's now go back. Okay, so that's exactly what I just mentioned. And then a final term is something called correct by construction. All right, correct by construction meaning that whenever we are constructing a model, no matter how simple it is, we want to make sure it is correct. And then when we refine one model to another, we want to make sure not only that F1 can satisfy properties, but also the refinement step is also correct. That's really the key. So that's called correct by construction, which is a very different approach than if you simply just dive into coding, maybe like what you did in the earlier programming courses. And then maybe if you really want to mathematically prove your implementation classes in Java is simply not feasible when you got so many classes. Final slides. How do we learn in this course? We're going to learn through case studies. So we'll study example models of programs or models of codes. Right? So we're going to see a lot of examples for models. Okay, in using a formal notation, which I'll mention at the end of the slides. And also we might do some proofs as well. And the example we're going to study will be from different domains. If time permitted, we'll try to cover all of them. We'll see. So we got sequential programs. So there's only a single thread of control. There's no concurrency, right? That'll be maybe the kind of closer to what you did, what you implemented in the earlier courses, programming courses. We're going to talk about concurrent programs. Maybe in your EECS3341, you learn about threading or like multi-processes. So there'll be interleaving processes that we have to consider for the concurrent program, which will be much more challenging than sequential programs. And also distributed system, mainly the system got possibly geographically distributed parties that actually have to collaborate together. Okay. And also we got reactive system, in which case the system rely on sensors and actuators. I'm pretty sure you know what these two terms means, maybe from EECS1021. And also we're going to use the Rodin platform. It's a theorem prover, right? Remember in this course we're going to use the theorem proving formal language to specify, right? The property to specify the properties and the system model. So we're going to construct a system model using the event B notation. So the textbook that we use in this course is called modeling in event B. So that's why in the very beginning of the slide I say MEB. So that stands for modeling in event B. It should be sufficient if you simply just study my slides and study my illustration and all the materials made available to you. But for those of you who may want to do some reading, feel free. The access to the PDF of the book draft is actually given to you. You need to log in passport you're logging to access the book, right? But don't distribute it. It's only for your personal private usage. All right, and then we're going to prove properties and refinements using classical logic, as I mentioned, propositional logic and predicate logic, and also set theory, including sets, relations, and functions, and the various operations on those constructs. All right, so that's about it for the introduction, and hopefully you have some slightly better idea about what the course is really about, and also how we can contextualize this course for you as a professional engineer. And for the second part for this week, we're going to start reviewing the relevant math for this course.